Okay, I'll be going through the chemistry assignment for salt preparation. So let's start. Okay, so let's look at the first question. The table below shows key information about the preparation of pure samples. So take note, it's a pure samples of different solid salts. So take note, it's for solid, pure salts. Okay, so they mentioned complete the table by filling in the missing information, including state symbols with any formula. So all these are already filled in for us already. So what you realize that they actually give you helping terms. For example, on this column, they actually want the formula used and formula of the reagents used, and you realize they also require the state symbol as well. So for the first one, so I got magnesium nitrate. How do I know is nitric acid required here? So this is actually your nitric acid. So how do I go about deriving this? So first thing, you must always know what's the method used to prepare the salt. So in this case here, magnesium nitrate, first thing I know it is a soluble salt. And because it's a soluble salt, I cannot use precipitation method. Okay? Second thing, I realize this magnesium nitrate, this is not a group 1 or ammonium salt. And because it's not a group 1 ammonium salt, I cannot use the titration method. So therefore, because of these two, I'm only left with the third method, which is acid plus excess insoluble substance method. Okay, and this substance that we are referring to, normally we are looking at either a metal, to be more precise, it's a reactive metal. We are looking at a carbonate, or we are looking at having it as a base. So base can either be your metal oxides, or it can be your metal hydroxides. So this is like a little summary in terms of what your three method of preparation. So knowing which method of preparation actually helps you to know what are the reagents you should use. So in this case, magnesium nitrate, I know that I should be using method 3. So acid is definitely what I need. Magnesium oxide is my base. So how do I know what acids I should use? So normally, the front part of the name, in this case magnesium, will form either the metal, the carbonate, or the base. So MCB. The back part of the name of the salt will give me my acid. So in order to get nitrate, the only acid I can use is nitric acid. And because it's an acid, it should be in the aqueous state. Okay, so that's for the first question. Second question is sodium chloride. So which method should I use? So you realize because it's sodium, it's a group 1 salt, therefore I will use titration method. So this one here, I'm going to use titration method. So for titration method, actually how to go about doing this is that I will normally need to have a soluble base or carbonate. Okay, soluble base or carbonate reacting with my acid. So what I know here is that Cl, the back part of the name will always give me the acid. So Cl will give me my acid. In this case, I know it's HCl because it's given here. The back part of the name, the front part of the name is sodium. So for it to be a soluble base or soluble carbonate, I can actually have two options. So the sodium can first thing either form my sodium hydroxide, which is my soluble base. The other one, it can also form my soluble carbonate. So the other possible answer actually is also Na2CO3 aqueous. Okay? So what are the the method used is titration, and you realize that this is actually like the steps also. So first thing for titration, obviously sodium chloride you know is using titration method because based on your because you have determined that it's going to use titration method. So the method used, you're going to put titration. Now once you have titrated the sodium hydroxide and hydrochloric acid, what you're left is your solution. Okay, sorry, I shouldn't draw bigger. Let me change this. Okay, because normally after titration is in your conical flask. Okay, so inside here I got my sodium chloride solution. So how can I get solid and pure sodium chloride out? So therefore, actually there's two ways to do it. You can either evaporate to dryness and you're left with sodium chloride, or you can do crystallization method for you to get your sodium chloride. So in this case, these two steps is trying to get your solid. You're trying to separate your solid from the solution. To be more precise, it is actually you're trying to get the dissolved solid out from the solution. Sorry, I wrote solid here. Okay, from the solution. Okay, SOL-N here, or this thing here represents solution. Okay. The last one is zinc carbonate. So now for zinc carbonate, if you look through the steps, you realize that zinc carbonate is actually an insoluble salt. And because it's an insoluble salt, why? Because all carbonates are insoluble except for group 1 carbonates or ammonium carbonates. Okay, so zinc carbonate, I know now I need to use method 1, which is the precipitation method. So how do I know what are the things I should use for my precipitation method? So my suggestion always is actually instead of zinc sulfate, right? My suggestion always is the cation of the salt, let it go with nitrate. So actually my proposal, instead of zinc sulfate, I'm going to use zinc nitrate. Okay. Then the back part of the name, normally I'll let it go with any one of the group 1 or ammonium cations. So in this case here, instead of potassium carbonate, I could also, sorry, this is AQ. I could also use potassium carbonate. I can also use ammonium carbonate as well. In general, what you want in terms of precipitation method, you want soluble reagent 1. You want your a soluble reagent add with another soluble reagent or reactant to give you your precipitate. In this case, that will be your salt. Okay. Now, the interesting thing is that your soluble reagent, one of them must contain the cation of your salt. It contain cation of salt. The other soluble reagent must contain the anion of your salt. Okay, so that's actually how you go about determining it. And of course, you know that this is called precipitation method. So first thing is, of course, precipitate the salt out. And next is to do filtration and obtain the residue. So residue is the solid. Okay, so take note of this first one. So this first one is actually a very good overview in terms of your salt preparation method. Okay, let's go on next. Next question. Dilute hydrochloric acid is added to 3 different test tubes containing substance A, B, and C. The results are shown. So first thing you see is that the different appearance of the solid. So I got green solid, black solid, and gray solid. When I add acid to them, okay, you realize A has a gas produced, and you realize gas form white precipitate lime water. So I know that A plus my acid, it will actually give out carbon dioxide. So what plus acid can give out carbon dioxide? You know that A must be a carbonate. B here is a black solid, no gas produced, so not much clue here that I can get. Next one, I know C is a gray solid. Now, whenever you see is a gray solid, you should be suspecting that it could be a metal already. But how can I confirm that it's metal? It's because you realize C plus acid gives me gas that extinguish a lighted flame with a pop sound. You know that this must be hydrogen gas. So what can react with hydrogen gas? What can react with acid to give hydrogen gas? C must be a metal lah. Okay. So these are some of the things that you can derive from here. Next thing, the color of the solution form. Now, this one you'll cover later on in your transition metals chapter. But whenever you see solution having color, you know that these two generally will be your transition metal lah. Okay, they will be the solution. The solution contains transition metal ions. Okay, transition metal ions. Now, what I will suspect is whenever I see pale blue, my antenna will come up, and I will suspect that this is most probably copper 2+. I'll put a question mark. Okay, so these are some of the clues. Then they say here, given that substance A is copper 2 carbonate, or copper 2 carbonate, suggest the name of the pale blue solution form. So if I got copper 2 carbonate, I let it react, react with hydrochloric acid. So that's hydrochloric acid. So what I will know is that I'm going to get, what's the salt form? The salt form is actually your pale blue solution. So this is actually the salt solution. I know that I'm going to get copper 2 chloride. I'm going to get carbon dioxide gas. And I'm going to get water. Okay, so that's how you go about getting the answer of copper 2 chloride. So take note, the 2 here is important. You must have it there. Next one, the blue solution formed in the reaction of dilute hydrochloric acid with substance A and B is the same. So they're trying to say that this guy and this guy here is the same. Okay? Suggest a possible identity for substance B. So it tells you that B must be copper 2 something lah. Okay? Now, so what could this be? It can react with acid. Okay? So B can react with acid to give you the solution. So in order for it to react with acid, I know that it should either be a metal, it should be a carbonate, or it can be a base, which is an oxide, or hydroxide. Now, because it's a black solid, I know it shouldn't be the metal. I know the green solid is carbonate, so that's A. So I'm left with either copper 2 oxide or copper 2 hydroxide. Based on your chapter for qualitative analysis, you know that copper 2 hydroxide, copper 2 hydroxide is actually a blue precipitate. So therefore, it cannot be a hydroxide also. Therefore, B, the only answer left is copper 2 oxide. Can? Okay, so take note of that. So you realize you need to be very familiar with acid reactions in order for you to do this properly as well. Okay, next up. Oxide of substance C can dissolve in aqueous sodium hydroxide. Suggest a possible identity for substance C. So I know that C is a metal, and then it can dissolve in aqueous sodium hydroxide. So actually, for it to be able to dissolve in aqueous sodium hydroxide, it means that it can react with alkali lah. Okay, I know C is a grey solid. I know C is a metal. So I know that C is a metal oxide. Now, which metal oxide can react with alkali? I know metal oxide, I got two main categories, as basic oxide, or it could be amphoteric. Now, basic oxide cannot react with alkali. Therefore, I know that the oxide of C must be an amphoteric oxide, which means C can only be zinc, or, sorry, let me use my favorite. So let's think of LACE. So it's either a lead-2 oxide, L, which stands for lead, or it could be aluminium oxide, or last one, it is zinc oxide. So there's one of these three, and that's why they ask you suggest a possible identity. Okay, and hence your final answer will be either zinc, aluminium, or lead because of the idea of the amphoteric oxide. Okay, that's how you go about doing part 3. Okay, next one. Okay, write a chemical equation for substance C with dilute hydrochloric acid. So if you choose zinc, this will be the answer, but you can also choose aluminium as well. So if you use aluminium reacting with hydrochloric acid, you're gonna get AlCl3 plus H2 gas. Okay, so this will be a bit more tricky, I guess. 3, I cannot put 3 here, so I'll put 6. Then I'll put 2 here. Then I'll put 3 here. Then I must put 2 here. Okay, so this is for aluminium if you're going to use it. Next one will be lead. Now, for lead, actually, is quite interesting because lead itself, in case you all forget, lead is one of those metals that actually, when it reacts with hydrochloric acid, so if I got Pb, when I react it with hydrochloric acid, I will get PbCl2, okay, plus hydrogen gas. So I put a 2 here, it's balanced. Now, problem is this guy here is an insoluble salt. So if I have lead, okay, in hydrochloric acid, HCl, this is my lead. In the midst of the reaction, okay, do take note, lead 2 chloride will form. So this blue color layer at the outer side is actually my lead 2 chloride. So as the lead react with hydrochloric acid, I'll form lead 2 chloride and it will coat my lead. So if lead 2 chloride coats the lead cannot react with my HCl anymore because they are no longer in contact. So the HCl and the lead is not in contact and hence they are not able to react accordingly. So actually the reaction will stop after a very short while. Okay, so typically this one yes, you can write because they ask you for a possible identity, right? So if you choose lead, this is a possible answer you can write. Okay, so A part 1, they ask you how you obtain a dry pure crystals from the solution. So what they want is they want copper 2 chloride crystals from your solution. So in general, it's crystallization. Obviously, crystals is a giveaway, right? So how to do crystallization? These are the general steps. Heat the solution till saturation. So the word saturation is important. So heat till saturation. That's the first mark. The second mark goes to cooling it down for crystals to form. So that's part 1. And subsequently filter the mixture to obtain the crystals. The crystals here are the residue. So do have the word residue there so that we are very clear that you know that the residue is actually the crystals itself. Okay, the solid is known as the residue. So this is the second mark. Now, you cannot just stop here because there's one final step where you are supposed to wash and dry. So rinse the crystals with a little cold distilled water and then finally dry with pieces of filter paper. So this is the rinse and dry step. Okay, so don't just rinse and dry. You must say rinse with what, dry with what. Okay, so sorry, I should tick all the points that you should take note of. Dry pieces of filter paper. So look at the mark allocation when you write down the steps for crystallization. Okay, so please don't miss out any of the points. If you ask me, I'll just say generally, actually there's 5 main points. Heat till saturation, cool the solution for crystals to form, filter to obtain the residue, which are the crystals, rinse the crystals with little cold distilled water, and finally dry between pieces of filter paper. Okay, so I'll see it as 5 different steps, but the mark allocation is as such, okay, in this particular paper itself. Okay, next one. The gas produced in the reaction with substance A dissolve in water to form a weak acid. So you can see here, we know that it's carbon dioxide form. So this gas that's produced is carbon dioxide. It dissolves in water to form a weak acid. So CO2, when you dissolve it in water, it actually gives you carbonic acid. Okay, carbonic acid itself. Now, what type of oxide is the gas? So in order for it to dissolve in water to form a weak acid, you know that this guy here is actually your acidic oxide. Okay, so that's the 1 mark. Okay, so being able to dissolve in water to form weak acid, you know that it is an acidic oxide. It's one of the properties of acidic oxide. Next, name the weak acid form. As I mentioned, this is already carbonic acid. Because it's name, you cannot write the formula, you must write the name itself. Next, write the chemical equation for the gas with lime water. So this equation here, please get familiarized yourself with it. So carbon dioxide gas, okay, will react with your aqueous calcium hydroxide, which is your lime water. In the exam, sorry, they won't be so nice. They won't tell you lime water is aqueous calcium hydroxide. You need to know. So when the gas is bubbled into your lime water, you're going to get calcium carbonate, which is your solid, and then water coming out from it. So these are all the state symbols. Now this question didn't ask for state symbol, and hence actually there's no need to write. Why did I write the state symbols? To let you know that actually your calcium carbonate is the white precipitate that you every time see whenever you bubble carbon dioxide into lime water. Okay? Next up. So Simon wanted to prepare a sample of pure dry lead 2 sulfate from lead 2 oxide. Now, to prepare lead 2 sulfate, I know I need to use precipitation method, because lead 2 sulfate is an insoluble salt. Now, as I mentioned before, in order for me to use precipitation method, I need to have 2 soluble reactant. Okay, 2 soluble reactant or 2 soluble reagent at the very start. Okay, so I need to have these 2 lah. Okay, I need to have those 2. But lead 2 oxide here is actually an insoluble substance. So I'm stuck. I cannot straight away use precipitation. I must do something about the lead 2 oxide to make it soluble. I need to make this soluble first before doing the precipitation method. Okay? So first thing, name a suitable acid which can react with lead 2 oxide to form a solution of lead 2 ion. So you can see here they're trying to guide you to try to let you know that you cannot just use lead 2 oxide for precipitation. You need to make it soluble first. So in order to make it soluble, actually the simplest way is you know that any single cation, once it's able to make it into nitrate, it will confirm be soluble. So all nitrates are soluble. Okay, all nitrates are soluble. So therefore, I will use nitric acid because I know lead 2 oxide is my base. It's a base. Okay, and I know that this can react with my nitric acid, which is an acid, to give me my salt, okay, which is your lead 2 nitrate. So once I got my lead 2 nitrate, life will be easier already. So then the next part is hence describe how Simon should proceed. So after you actually react with nitric acid to get your lead 2 nitrate, how should I proceed in order to obtain the maximum yield of pure dry sample of lead 2 sulfate from lead 2 oxide? So first thing you need to do is add excess dilute nitric acid because you want all the lead 2 oxide to react. Okay, so add excess lead 2 nitrate to add excess dilute nitric acid to lead 2 oxide, okay, to react with the lead 2 oxide completely. And what you're going to obtain lead 2 nitrate solution. Okay. Now, to the resulting solution, you're going to add excess dilute sulfuric acid or any aqueous sulfate. So what are the possible aqueous sulfate? You can actually add sodium sulfate, you can add potassium sulfate, or you can also add ammonium sulfate. Either one of these also can. So once you add those 2, you're going to have your lead 2 sulfate being precipitated out. So you realize first thing is to get your lead 2 nitrate. That's the first step by adding excess acid. Next is just to mix them together so that you can get your salt. Okay? So this is step 2. Once you get your salt out, you realize your salt is still in the beaker. Okay? That solution is solid. This is my lead 2 sulfate. So how can I get my lead 2 sulfate out? If it's a solid in a solution, the next step obviously is to filter. So you'll filter the mixture to obtain the residue. So you realize the residue here, okay, which is your lead 2 sulfate precipitate. And the last step is to rinse with distilled water and then to dry with pieces of filter paper. So rinse with distilled water, dry with pieces of filter paper. Okay? So this is the marking scheme here. Every 2 points, one mark. So there's actually quite a few points over here. Just make sure you take note of them. Okay, last one. Write an ionic equation for with state symbol for the formation of lead 2 sulfate salt. In general, I'm just going to show you like the reverse engineering method. So I know lead 2 sulfate is an insoluble salt. So I'm just going to write PbSO4 solid. Okay? Now, I know that the 2 things I added at the start definitely must be equals. So I'm going to add 2 things at the start equals. And because it's an ionic equation, I just need to focus on what are the ions that contributes to it. So in this case, it will be lead 2. And then the other one will be sulfate. Okay? So this is actually the ionic equation for the formation of lead 2 sulfate. Now, because they ask for state symbols, so you need the state symbols all to be in as well. Okay, last one. Or for this one, I think, last one, right? Okay, so Simon then attempted to prepare a pure dry sample of ammonium nitrate salt. He then used the following procedures. Okay, so there's a lot of steps here. So actually to prepare ammonium nitrate, you know that you should use titration method. And hence you realize he mentioned about burette and stuff like this. Okay, so where are the issues in this? Because the question is, oh sorry, I realized I haven't yet. Okay, so you use all these procedures. So the first one is state the color change of the indicator. In this case, it's methyl orange. That was mentioned here. So it was added to the conical flask, and conical flask actually contains aqueous ammonia. Aqueous ammonia is an alkali. So what is the color of aqueous ammonia when the methyl orange is added? So methyl orange will actually turn to, will be yellow lah. Okay, methyl orange will be yellow in the alkaline solution, which is purely your aqueous ammonia. And then orange is actually the endpoint, okay, of neutralization. Okay, that's why it's yellow to orange. Now, if it is starting from acidic, so if it's starting from acidic, it will actually start from red. Okay, so just take note of the different color changes. Next one, suggest a reason why activated carbon was added to the solution in step 3. So you realize actually in part of your titration method, you are supposed to repeat the titration without indicator. Normally, after you do the first time titration, you're supposed to repeat the titration without indicator for the second round. But in this case, there's no repeat. They just add the activated carbon, okay, and then warmed. So what's the purpose of repeating titration? What's the purpose of acting this activated carbon? It's really the key idea of not having the indicator. So what's the problem of the indicator here? The indicator is actually an impurity. Because why? All you want is a salt, but if you got an indicator there, that color actually is an impurity causing your salt not to be pure. So why should you add the activated carbon in step 3 is really to remove the indicator in the solution so that you can have your pure dry sample of ammonium nitrate salt. So state what you do if step 3 was not carried out. So obviously they're saying, okay, what if you don't want to use activated carbon? What can you do to remove the indicator? Just repeat the titration using the same volume of acid and alkali, but not using an indicator. So literally, because you already determined the endpoint, you know how much acid and alkali to use, and hence you could just repeat the same experiment without using the indicator to get your pure dry sample of the salt. Okay, so why is step 4 not suitable to obtain ammonium nitrate? Heated to dryness. Normally when you heat to dryness, but then they say it's not suitable, generally it's because the salt will decompose. Okay, so not decompose. Oh, I realized I spelled wrongly. Sorry. So what you realize is that you see step 4 is about heating to dryness, and they say it's not suitable. Generally, it means the salt will decompose upon heating. Okay, so it will undergo thermal decomposition. So it's not thermally stable and will decompose on heating. So the key word here got two parts. One is it being not thermally stable. And because it's not thermally stable, it will decompose on heating. Okay? So that's for this part over here. Okay, next. Next one. So this one is a little bit more on the data portion of things. So let's read through. So the pH meter and data logger is used to monitor the pH changes in 2 different titrations. So I got 2 different titration, and I'm monitoring the pH change. Okay, let's continue reading. They say sodium hydroxide is added from a burette. So in the burette, I know I have my sodium hydroxide, which is alkali. Conical flask contains my hydrochloric acid. Okay, conical flask contains my acid. Now, titration 1 contains dilute hydrochloric acid. So HCl for, let's call it T1. Dilute ethanoic acid in titration 2. So I know that ethanoic acid is CH3COOH for T2. Okay? Now then the question is, what's the difference between these 2 acids? Normally when the question is set, they do 2 different experiments. If both are acids, that means there must be some difference in the acid, right? So in this case here, actually HCl and ethanoic acid, when you see these two coming out, generally is a strong versus weak acid kind of concept that they may be trying to test you. So hydrochloric acid is a strong acid, ethanoic acid is a weak acid. So it's the whole idea about completely ionize or dissociate to form H plus ions. Whereas for weak acid, it is partially ionized. So strong is completely, weak is partially ionized, blah, 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 blah. Okay? So both will form H plus. One is it will completely ionize or dissociate. The other one, weak one, is only partially. So the word completely and partially are like your keywords. Okay, next, during the titration, the pH value changes. So if I look at the graph, okay, I can see the pH value, you can see flat, then goes up all the way, and then it becomes 13. So from 1 to 13. Okay, at the end point of during titration, whereas for this one here, you realize it starts at about 2.5. It gradually increase as more and more alkali is added. Then at 20, there's this sharp increase. Then it will end off at 13. Okay? So the question says at the end point of titration, there's a drastic change in the pH value. So where is the drastic change? This is the drastic change over here. This sharp increase. So the end point is actually a volume. So 20 for sodium hydroxide, 20 for titration 2. Same thing, 20 for titration 1. Okay? So interpret the thing accordingly. So you can see here, all here, everything is here. They mentioned that indicators can also be used to determine the endpoint of a titration. So instead of looking at the pH curve using a pH meter and data logger, I can actually use indicator, which is generally what we have been doing in the lab. The endpoint happens, when the indicator changes color during the drastic change. So take note, it's not about indicator changing color means endpoint. The indicator changes color during the drastic change. So you realize for T1, the drastic change happens between, let's start from here, pH 2 to about pH 12. So T1, the pH change from 2 to 12. So this is the range that the pH change. Whereas for T2, realize it is from here to somewhat about here. So the pH change is really between where the endpoint happens is from about 8 to 11. Okay, 8 to 11. Okay, so this is how the things are in terms of the pH changing. Okay, so they say the diagram below shows the colors of some indicators at different pH. In between the colors, indicators change color gradually over a range of pH value. Okay, I say again, in between the colors, so in between the colors, okay, the indicators change color gradually over the range of pH. So this part here, this part here, this part here, in between the colors. Okay? As indicated. Okay, so state two differences between the pH curve for titration 1 and 2. So you realize that there's actually a few segments you can talk about. First is the initial segment. You realize that for titration 1, the pH is relatively constant at about pH 1 until the endpoint, where it has that sharp increase. Whereas for T2, the pH is gradually increasing, and at the endpoint, the pH will suddenly go up. That's the first thing. Second thing, titration 1 starts at pH 1, titration 2 starts at pH 2.5. Okay? Next thing you can observe as well, you realize is that the endpoint pH range is very big for titration 1, whereas the pH change at the endpoint for titration 2 is really relatively small. So these are some of the things based on just offhand looking at the graph, you can roughly get it ready. So if you look at the answers here, so you realize the pH change, the drastic change in pH for titration 1 between 3 to 11, but then for titration 2 is between 8 to 11. Okay? Next one, the pH remains relatively constant, okay, before the endpoint in titration 1, but there's a steeper increase in titration 2, okay, before the endpoint. So the first point is talking about the yellow color. So actually, this thing refers to the yellow part about a sharp change. The second point about being relatively constant is talking about the blue part. Okay. Next one, the initial pH, okay, which is the green part that I've highlighted. Okay. This endpoint here actually refers to the middle. So to determine the exact pH of the endpoint, actually you need to look at the middle of the graph. So, between here to here was the middle point. So that's how you go about determining it lah. So it really is the middle of this whole range here. I think it's here lah. Then this one will be from here to here, the middle point. Okay, that's how they go about finding out this value over here. Okay? So what's the pH of salt solution? Actually is linked over here. So pH of salt solution after titration 1 will be pH 7. Which type of graph would you expect if titration between potassium hydroxide and dilute nitric acid? So you know that this is also similar to sodium hydroxide. They are both strong alkali. Dilute nitric acid, you know, is a strong acid. So actually, this is very similar to strong acid, strong alkali, and hence it is about titration 1. Okay, so take note, this is strong alkali with strong acid. That's for titration 1. So that's how the curve will look. For titration 2, this is strong alkali with weak acid. Okay, then of course there's a other combination of weak alkali with strong acid, weak alkali with weak acid. But that's not covered here in this particular question. But those are two other graphs that you can see in terms of your titrations as well. Okay, now part D, part 1, explain why methyl orange is not suitable for use in titration 2. So you know that indicators, okay, what's the purpose of indicators is that they will change color during the drastic change. The question asked is, in titration 2, I want to use methyl orange. They say it's not suitable. How come? So first thing first, I look at methyl orange. The change happens between pH 3 to pH 5. Okay, this is my indicator changing color. So my endpoint must be between 3 to 5 lah. Okay, in order for my methyl orange to detect that, to have that color change to show endpoint. But what happens is that you realize for titration 2, the pH change happens from about 8 to 11. So the indicator color change does not match the pH range, does not, oh sorry oh no, oh no, oops, I realized the whole thing gone, sorry guys. Let's go. I wasted, but never mind, at least it's recorded, so that's good. So I just want to highlight what I wanted to write just now was this. It was that the pH of color change of indicator does not match the pH change of the drastic change. Okay, so just take note of that, and hence this is the answer here. You realize it's trying to match the change in pH of titration 2 together with the color change pH as well. Okay, now so name a suitable indicator that can be used for titration 2. So I want to make sure that my indicator changes color between 8 to 11. So let's go back to here. You realize that the only possible one, even for litmus, cannot, because litmus is between 6 to 8. So what I want is actually to use phenolphthalein because it changes between 8 to 10. So this is within, there's overlapping range between the indicator and also the titration drastic change. Okay, so yep, so that's for going through of this answers here. So that's